Welcome everyone. Today we're going to be explaining multicollinearity and associated diagnostics. Let's get started. What is multicollinearity? Well, it occurs when two or more independent variables in a linear model are closely related to each other. This is when they're too closely related. They overlap. You can't pinpoint which one is affecting the outcome or the dependent variables. Does one have more an effect over the other? You won't be able to tell.
Next, we're going to be talking about how multicollinearity is calculated in the associated diagnostics. As you can see, we have some formulas to the side here that can help us identify the correlation of the multicollinearity. The first step that you would take is to regress x1 on other independent variables. This equation is shown in the bottom right, where you can see y equals x0 plus x1 times b1. This is just the regular regression equation. The second step is to plug that value you find into the VIF formula. VIF is the variance inflation factor. This equation is the final calculation to solve for multicollinearity. The final step of this process is to solve for VIF. The VIF then tells us how correlated the independent variables are. If the variable has a high VIF, it means it is highly correlated with other independent variables. A VIF of 1 means no correlation is seen with other variables. An example here is a VIF of 6.67. This means that the variance of the regression for that variable is 6.67 times larger than it would be if there's no multicollinearity shown. Therefore, this is how you solve for multicollinearity, and I hope that helped.
There are several types of multicollinearity, for example, structural and data-based. These are some examples of data-based multicollinearity that is the type that we encounter most often. Now that we understand a little bit about multicollinearity, let's look at some examples. So, our first one. Think about looking at what makes families buy more ice cream. Some stuff we might consider: how hot it is outside, how sunny it is outside, and maybe the number of ice cream trucks in the neighborhood. What's tricky about this is sunny days and hot days often happen together. So those two variables overlap and move together. This is multicollinearity. So it's very hard to predict which one really matters when you're thinking about ice cream sales. But when you're thinking about the number of ice cream trucks, it doesn't depend on the weather, for example, with our other two variables, so it's much easier to see their effect on whether this makes families buy more ice cream. Another example we can look at is predicting wages based on years of education and number of degrees. This can also be an example of multicollinearity, because those with more degrees usually spent more years in school, so it's hard to separate their effects on salary. So these two examples kind of show us that when our predictors move together, so when it's sunny outside, when it's hot outside, or whether you have more degrees and spent more years in school, their individual effects on the outcome variables become harder to separate. If you also look at our image over here with the overlapping circles, this is a visual representation of how multicollinearity works. There's less dispersion of the independent variables, leading to more of an overlap in their effect. This means it's hard to differentiate again, whether it's affecting the dependent variable. I hope that helped. Thank you for listening. Now that we understand, there are several types of multicollinearity.
Let's wrap this up and simplify it. Multicollinearity is when two or more variables are occurring at the same time that are too similar. This makes it so you are unable to determine which variable is the true cause for the outcome. The VIF, or variance inflation factor, is how this can be detected. The number you get when calculating VIF tells you how many times larger the variance is due to this multicollinearity.